Welcome. My name is Peter Dourmashkin, and I'm a senior lecturer in the physics department at MIT. And today I would like to talk about our blended learning class at MIT. So I'll begin by sharing my screen. So today I'd like to describe our blended learning program at MIT. It originally was called Technology-Enabled Active Learning, or TEAL. This has been a 20-year experiment at MIT in which we've introduced active learning into the classroom. It was developed by Professor John Belcher, and it was designed for first-year undergraduate physics students, all of whom have to take two semesters of physics at MIT. So these are large classes. The TEAL classroom is designed for active learning. In this picture, you can see I'm at the center. Students are working right now in group problems at the whiteboard. And the most important first principle that we want to have is what are our learning objectives for the students? Now, there's two types of objectives. We have physics objectives in which we want the students to understand that the principles of physics form a coherent set of ideas based on experimental evidence that describe the world, models for the physical world. But we also want to develop strong problem-solving skills, both analytic and conceptual. Those are our physics learning objectives, but we have a lot of other softer learning objectives. We wanted to move away from a passive lecture format to an interactive environment. We wanted the students to develop strong communication skills, skills that they would need when they graduated from the university in any type of occupation. Most importantly, we wanted them to develop collaborative learning, something that they need everywhere. Learning how to ask questions, to answer questions from their peers, together to work on problems to achieve the collective group mindset. We also wanted to encourage undergraduates to teach, and this was a very important part of our program. And finally, we wanted to develop a mentoring program for our students. And I'm going to talk about a lot of these features today. But before I get into the details, one of the most important things is about the learning space. What are the design principles? And in my mind, it's really important to base the architectural design of a classroom on how people interact and learn. So in our classroom, we don't have a lecture at the front and seats. We have round tables in which students can sit opposite each other, ask each other questions, work on problems together. They have whiteboards in which they can go and draw their solutions so that the teaching team can circulate in the space and help them learn. The second really important thing is about course design. Now, traditional course designs start with a content. There is a textbook. In the first semester, you teach chapters 1 to 19. In the second semester, you teach chapters 20 to 40. And this is a course that's defined by the content. At the end of the course, you have assessment. This is the traditional way of designing courses. Backwards course design is a different concept, a very interesting concept. What you first decide is what are the learning objectives? What are the outcomes that you want to have for your students? Then, what is the acceptable evidence that the students have achieved those desired outcomes? And finally, how can you design the instructional approach to achieve those outcomes? So here, the course content is determined by the outcomes. And that's why it's called backwards course design. For us, we have this blended learning, which is also called the flipped classroom model. And I'd like to spend some time describing the various features of this. This is nothing radical or different than what people often do anyway. So there's basically three components: pre-class, which is students do before, in-class, and post-class. And the in-class part is active learning. And now I'll talk about each of these separately. But to begin, I want to explain our modular learning sequence. So each week, our sequence begins with 2 online learning sequences due before the first class. The first active learning class is on Monday. So in these 2 online learning sequences, this is where students are getting content. I'll describe these learning sequences in detail in a moment, and it prepares them for class. If you like, it's reading the book. Then after the first active learning class, there's 2 more online learning sequences that are due before the second class. The second class is on a Wednesday, and that's again an active learning class. The third active learning class is on Friday. It's devoted to just problem solving, having students develop practice. And then after this week sessions, they have a problem set in which they have homework, and that's due the following Tuesday. The learning sequences, so let's talk about each of these elements in turn. But what's absolutely crucial was that we had a platform, which was our MIT-X platform, in which we could put all of our learning sequences on, we could put all of the in-class material on, we could put our problem sets on, we have course information. Now, many of you have, there's a lot of platforms out there that people use for classes, and this is the one that we used. And I'll talk about some of the features as we go along. So here's more detail about the structure of the blended learning. Our pre-class, there's 4 learning sequences during the week. Each learning sequence is approximately 1 hour. And this covers the content of the course. We have the in-class, which can be both in person or online, as we had to do with the COVID crisis. These are 3 one-hour classes. The first 2, the faculty lead it, and there's both discussion and group problem solving, concept questions, a variety of active learning activities. And the second one is the third one, the workshop, is strictly students working together in groups on problems. And then the post-class, as I said before, is a problem set, and also they have take-home experiments. So that's our blended model. And now let's look in detail at some of the features. So for the pre-class learning sequences, we used, again, for the delivery of content, we developed about 400 short Lightboard videos. I'll explain what Lightboard means in a moment. And these videos and readings are very short, 4 to 8 minutes. They're interspaced. Each video may be followed with a short analytic problem or a concept question. And there's about 8 to 10 of these activities for each learning sequence. Now, what's crucial here is that in terms of the content, students can work through the material when they are ready to learn, not in class. Now, we all know that not all students attend class, and even if they are attending, they're not always paying attention. And so here we grade these learning sequences, and they can do this on their time. Now, I'm very lucky that we grade this. We expect that we've established a culture in which this is expected of our students to do this. That took some time. And this was a very important part of the blended learning. We use these Lightboard videos, which is a very nice tool in which to develop videos. They come with transcripts. And here I'm going to show you an example of a Lightboard video. Here I am describing a physics topic.
We looked at the change of potential energy for a spring when it went from some initial state to some final state. So let's just reintroduce how we describe that. Here's a spring. And let's call this our initial state, x equals 0, I hat. And our final state, we chose to be either stretched or compressed. And we define this to be the stretch in this particular case. And we know that the spring force in this coordinate system, F equals minus kx I hat, is always restoring the system back to equilibrium. So whether you stretch it or compress it, the change of potential energy should be a positive quantity. And we calculated that to be equal to the difference in potential energy between our equilibrium state and our initial state. We'll just call that equilibrium position. And some stretch state was 1/2 k x squared. Now, if we choose.
So I'm going to stop the Lightboard video here and just go to the end. This video was about 4 minutes and 45 seconds. And you can see at the end that I've graphed out the potential energy function and talked a little bit more about this. Students can see this video on their own time. They can repeat it as many times as they need it. And what follows up on this video are short questions about both the concepts and the application of the ideas that I did in the video. Now, what I like about the Lightboard is that there's a lot of nonverbal clues in teaching that aren't just what's written on the board. Where my hand goes, where my eyes are going, my expressions, my other aspects of how I'm communicating, all of these things can engage the students and help them motivate to learn. And I think it's a very powerful tool. You can actually look up Lightboard. Here's our Lightboard studio online, and you can see how to build a studio. They're actually not that expensive, and they're especially useful. So it's really well worth the money in developing these Lightboard studios. Here's the screen. We have a camera and a computer console where my colleague and I work together to develop these videos. In about 2 hours, we can make about anywhere from 6 to 8 videos, short videos, and get them online almost within 15 minutes after we've stopped recording. Now, once we introduced this Lightboard Studio, it became very popular at MIT. And now we have something like 4 studios. And faculty members are even building studios in their own offices so that, given the pandemic, they can make these videos very quickly and very inexpensively. So it's a very powerful tool. Now let's turn to the in-class. It can be the synchronous session, whether we're residential or online. And in this session, the faculty lead the active learning. This is all about understanding content, and it's focusing on engaging the students through practice. We have 3 different 1-hour sessions. 2 are led by the faculty, and there's discussion, and the faculty is basically prompting a lot of issues. And the third one, the workshop class, is all about skill development with an emphasis on practice. The faculty do not lecture. In fact, it's the graduate students who run that class. And all of these classes are built on the principle of active learning. Now, there's lots of different types of active learning. So I want to just take a little bit of time to describe why we think it's so important. In particular, to develop, one of our outcomes that we want is to develop expert problem-solving skills on the part of our students. At MIT, students will solve about 10,000 problems. Some are very easy, and some are undergraduate theses. And all of that experience in solving problems gives them confidence that they can solve any problem. Now, obviously, that's not always the case, but it's this confidence built on practice and experience is necessary for innovative and creative thinking. And when we want our students to graduate from MIT, this is one of our most important principles that cut across all aspects of the MIT undergraduate education, is to build expert problem solvers. Now, we do it for the first year very simply with group problem solving. So when we're in person, the students are working together in groups at a board. Our teaching team is helping them. They're getting feedback from the instructors. When we were online, it was more complicated. And we were very lucky to, again, have a digital tool. It was an app, a peer-to-peer app called Explain.Education, actually developed by an MIT student. And this app was designed to enhance group interactions. So what we did is we created 15 groups on the app. The students were assigned to groups. So they might be assigned to 0, 1, 2, 3, et cetera. They have a board and a stylus. Now, obviously, this is an issue about, do students have pads and styluses? But again, we were very lucky. MIT had a loaner program where they loaned out pads and styluses to any student that didn't have one. This video has sound, and this app has the capabilities for both sound and video, so students can see each other. And when they're solving problems during these in-class sessions, our teaching team went into the individual groups and talked with students and helped them. Our undergraduate TAs were assigned 2 or 3 groups, and our other teaching team would circulate amongst all the groups. In the app, I could see what all the students were doing at once. So what was on every single board, so I could go into the rooms as needed. And this was just a wonderful tool for bridging this gap during online in-class synchronous sessions. One thing I want to mention, though, is the importance of these designing group problems and balancing the challenge versus skill level. if students start off in this graph, we have challenge in the vertical axis and skill horizontal. And at the beginning of a course, when the skill level is low, if the challenge is too hard, students get discouraged and lose motivation. Likewise, in the beginning of the course, if the challenge is too easy and their skill level is too high for that challenge, again, students lose motivation. So part of designing all of these group problems is this target zone of having the challenge and skill levels balance. And as you advance in the course, you can raise, as the skill level raises, so does the challenge level. Now, we used Eric Mazur's concept tests in the class. He developed a methodology that involved asking a question. Students think individually, they answer individually. We use our MIT platform to record their answers. That way, as a teacher, I can see whether or not they need more time. That's what's called just-in-time teaching. I can decide on the spot how much time I want to spend on this concept. Then after they've individually answered, there's peer discussion, and they can revise their answers. During the peer discussion, our teaching team circulates amongst the students, and we sit down with them when we're in person or we're in their explain room when they're online, and we talk with them about the concepts. We ask them to say what they think is right or wrong in other answers. And this is a very important process in which to develop both communication skills and conceptual understanding. At the end of the process, there's lots of ways to have explanations. One of the most important things is for the students to discuss and present their process of thinking to the whole class. They can give answers. They can talk about what they thought was right or wrong. So, or separately, the instructor could say, would you like to hear how I think about it now that they've gone through this process? And so the instructor can then bring closure to the whole process. This concept tests have now become used all over the United States and also lots of places I know in Brazil and around the world. One of my favorite concept questions is this: if you have a beaker with water in it and you have a boat with a rock floating in the beaker and you measure the water level and you take the rock out of the boat and put it at the bottom of the beaker, does the water level go up, go down, or stay the same? I'm sorry, does it? Yeah, the three possibilities: high, the water level higher, the same, or lower when the rock is at the bottom. Now, this particular question is an example of Archimedes' principle, the famous principle where he shouts "Eureka" in the bathtub. And it's a great concept question. It initiates a lot of discussion. Once you have students responding, I can see on our MITx platform what their responses were, and I can decide, for instance, in this case, at first, the green was the right answer. It's not the same question I just gave you. Lots of students had it wrong at first, and after discussion, their answers improved. And then there was closure to the process. There are other types of activities that you can do in the class. We use a lot of visualizations and simulations that we develop. This one is a discovery activity in which we set up an app in which students can discover Faraday's law, a law about changing magnetic flux and inducing a current. And we don't tell them what the law is. We ask them based on the data to see if they can make conjectures and then test their conjectures to see whether the law is correct. There's a wonderful set of simulations in Portuguese, the Brazilian version. They're called PhET simulations developed by the University of Colorado. These simulations come with learning modules that were designed by education specialists with concept questions and problems. They're a wonderful set of simulations that can be used online at any part of blended learning, pre-class, in-class, or post-class. I highly recommend them. So post-class, I just want to point out, we talked about this a little bit already. MIT's, a big part of MIT education are called problem sets. And we have about 6 problems. Students can work either individually or with their peers, but they must submit their answers, their individual answers for grading. We also have as part of the post-class take-home experiments. And if it's a week in which there's some type of assessment like an exam, they'll have review problems and a whole bunch of other information in the post-class. So this is really the structure of blended learning, but it's not just the structure that is crucial. The digital tools that we use are essential. And as I said before, the MIT platform was essential. For example, in the homework, there's an answer checker on the MITx platform. So when students are working on their own and they're not sure whether they have the right answer or wrong answer, they might submit their answer, and here 2 of the answers were correct, but the third one was something was wrong, and the software tells them about that. It doesn't give them the answer, but it tells them that their answer was wrong. And our students all thought that this was an incredibly useful tool that helped motivate them to get to the right answers for the problems. Now, given all these aspects of blended learning, what's still crucial is we wanted to have some type of experiential learning. So these are the take-home experiments where students would have, in this case, they had to design an apparatus that would measure the period of an oscillating bob in a simple pendulum. And they had to measure the period, and then they had to have a model and see whether or not their results corresponded with the model. And if not, how could they test that model and change their apparatus to get a better agreement with the model? For instance, with pendulums, there's a big difference if you just pull it out a little and let it oscillate, or pull it out a lot and let it oscillate to measure the period. And so the idea here was they needed to design, build, and modify their experiment based on their data and the model, and they had to analyze it. All right, so in the active learning class, what is the role of teachers? So in my mind, this is a little bit different. We're information providers, motivators, and we can be mentors. And so in the motivation and design part, we have to design content that matches challenge and skill level. During the active learning, we circulate, we give guidance. And at the end, we provide an opportunity for either the students or the teacher themselves to bring closure through explanations, and we measure learning outcomes. Now, what's, again, essential thing that we want to accomplish during the COVID era was to try to create a community in a blended learning class. Now, our community consists of the following parts: the faculty member, graduate teaching assistant, undergraduate teaching assistants, our curriculum development support team, the students themselves who are peer instructors, our technical staff who develop experimental tools and help with the learning during the active learning, and the mentors that we introduced. So this was our teaching team, but how do you create community? Well, first off, faculty need to be trained. This is absolutely essential because many faculty are not used to this model. And if they're unhappy with it or they have legitimate complaints about it, that can undermine the whole community right from the very beginning. So faculty training is essential. One of the things that transformed our classroom culture was the development of undergraduate teaching assistants. At the end of every semester, I write a note to the students who just finished the class. Can you nominate your peers who helped you learn? I get something like 100 nominations in an hour. So we tried to create this prestigious position of undergraduate teaching assistants. The students either get credit or they get paid. And this transformed the student culture because it provided an intermediary between the students and the teaching team. And it also gave our undergraduates an opportunity to relook at the material, which is really, as we all know, when you teach, you're also learning. So we introduced a mentoring program due to COVID. We were really worried that our students would get lost in the online world. And our mentors were graduate students, faculty, technical staff, undergraduates were the bulk of the mentors. They met with their students about a half an hour to 3/4 of an hour a week. And the mentors were there to discuss with them best study practices, to answer specific physics questions, but also they were there to help them with any personal issues. They were there really to motivate the students. They were there to listen to the students and help the student reach solutions to their problems. They were information providers at the same time. What was essential was weekly training meetings, which we called community of practice. And during these training meetings, we focused on 4 different things. We focused on the cognitive science of learning, what it is we actually do in the classroom. We talked about metacognition, how we prepare for class. We talked about active listening. How do we listen to our students to hear what their goals are and to help them reach those goals? And most importantly, we talked about belonging. Are we actually in the class? Many students feel they're excluded from day one. And this belonging is a really crucial process for helping students motivate and helping them learn. Our crucial part was institutional support for open learning at MIT. In this flow chart, there's a bunch of things here. All I want to do is highlight the left side, which is the digital learning, the Dean for Digital Learning. And in there, for our residential education, we had a digital learning library. We had our platform, MITx. OCW is OpenCourseware, where people all over the world can find things. We have international reach out, JWEL. All of this was a commitment from the institution about online open learning. But again, another really crucial element was to have, and I think all universities should have something like this, which is a teaching and learning laboratory. This is a resource center. It helped me in the course design. It can provide assessment strategies. I turn to them when I want to know how to design rubrics for group learning. They help us, and they ran a lot of our teacher training and mentor training workshops. It was founded by Lori Breslau. Now Janet Rankin is the leader of this. This is an incredibly useful tool for teachers who are not education specialists to help them resolve many of the issues that they'll face in the classroom. So I want to end by saying that our goal is to develop lifelong learners. That means that the university should not just be about giving students specific knowledge which can become outdated very quickly, but it's about developing lifelong learners, about developing the thinking tools that students can solve problems, they can feel motivation and confident to address new circumstances, because we live in a world in which there are a lot of big problems that we can't anticipate, like COVID or something like that. And our students need to know how to rethink and to change very rapidly. And that's really this process of becoming lifelong learners. So I want to thank you all for listening. I know I spoke very fast, and I apologize that I'm not speaking in Portuguese, but I hope that this was interesting, that I could share my experience at MIT, and that this could be a starting point or a point of departure for you to think about any of the things that we did that might be helpful in your environment. So thank you very much. And now I'd like to say goodbye.